Hello Math 13-14 students. Let's begin lesson 6, linear functions and linear models. Well, at least that's the title, but we're going to do far more than those. We have to cover some fallout topic from lesson 5, section 1, library of functions, that one first, and then we're going to study linear functions from section 2. Alright, let's begin section 1, library of functions, and let's study some well-known functions. First, power functions, which can be subcategorized into 4. The simplest case, x to the nth power, where the power n is a positive integer. Depending upon whether that positive integer n is odd or even, we get either blue graph, which are odd functions, and green graphs, which are even functions. Blue here, x to the odd power. Green down here, x to the even power. You're looking at x to the first power, third power, fifth power for blue, and second power, fourth power, and sixth power for green. And do you see any symmetries there? Of course you do. Blue graphs are all symmetric about the origin, and green graphs are all symmetric about the y-axis. And the reason is, of course, negative x to the odd power is negative x to the odd power. Negative x to the even power is just x to the even power. Negative just disappears. So we have something here to the right. Flip over to the negative x, we have to have exactly the same replica there. This time, flip over and then flip over y as well, then we get replica there. So we have symmetry about the origin for blue, symmetry about the y-axis, green. Another way to see those, well, if you move to the right, some humongous to the odd power, yeah, okay, that's going to be humongously positive. If you move to the left, something humongously negative to the odd power, it will be humongously negative. Negative to the odd power is negative. So graph goes down this way, up that way. So overall, increasing, strictly increasing. Now what if you have even power? Well, let's move to the right. Something humongous to the even power, yeah, okay, humongously positive. How about this? Something humongously negative to the even power, that's going to be humongously positive. Negative to the even power is positive. So either way we have going up to infinity. Overall, decreasing and then hit local minimum, which is absolute minimum as well, and then increasing. So here, decreasing and then increasing. Minimum here. Here, strictly increasing all the way. So that's what you're looking at from the graphs. And here's another feature. Look at the slope, steepness, or flatness, whatever you may want to call. Do you realize that as the power gets larger, first power, second power, third, fourth, fifth, and sixth power, the graph gets flatter and flatter and flatter around the origin. Also, as I move away from the origin, to the right or to the left, graph gets steeper, steeper, steeper as n gets bigger. You can understand those kind of behavior like this. When x is pretty small, which means x is pretty close to 0, consider these 0.1, 0.01, 0.001. Those are the x values. And then if you take the first power, then y value will stay the same. So 0.1 stays at 0.1, 0.01 stays at 0.01, and 0.001 stays at 0.001. Nothing fancy. We just go down to 0. That's what happens for the first power. Now what if you have the second power? X coordinate is 0.1, 0.01, 0.01. The y coordinate is square of those, so 0.01. 0.00001, and then like that. So basically we are doubling the number of zeros each time. So y coordinate value is getting much faster, getting down to zero much faster. And consequently, the curve gets down to the x-axis much more quickly. So you have flatter, even flatter, even flatter, that kind of behavior. Now, if you move away from the origin, things are opposite. Consider x value 10, 100, and 1000. First power, they stay the same as 10, 100, 1000. If I square them, you get 100, 10,000, and a million. And to the third power, you see the picture. They're going to grow far more quickly. And then if you look at these graphs, growing like this versus getting steeper, 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 even steeper, even steeper, you see those kind of behavior. So they have a lot to do with how quickly they are growing, how quickly they are decaying. So around zero, quickly decaying towards zero versus outside away from zero, how quickly blowing up to infinity or negative infinity. You're looking at that kind of behavior. Such a change is important in calculus. Here, just remember those kind of behavior and the fact that we discussed it. For now, just focus upon the graphs. The second category, the power is 1 over n. In that case, we have radical functions. Here, second radical, so square root, and then third radical, so this cubic, and this is fourth root and fifth root, etc. Or the even root function, square root, fourth root, sixth root, those kind of things have validity, valid domain only for x is greater than or equal to 0. Because you see, y squared is x, y to the fourth power is x, kind of like that. Yeah, we have to look at green, excuse me. And there's no way I'm going to get a negative number by taking a square or fourth power or sixth power and so on. So the domain is only to the right. As for odd radical, yeah, negative 10 to the third power is negative 1000 and so on. So yes, there are negative numbers. You can consider negative numbers. That's the way our textbook author does. But once you step outside this 13-14 classroom, once you get to advanced mathematics, just 2000 level, not too much, just 2000 level or up. And whenever you have a radical, x will be considered non-negative. And even very rarely we are going to consider 0. For square root of 0, yes, we do, but others, even zeros are rarity. We don't consider negatives. So most of the time, you can just discard this left-hand side part. I'll just follow the textbook's expression to consider the left-hand side here, but because it's not really widely accepted outside this 13-14 classroom, I'll never write exam problems or anything like that for cubing root or fourth root of negatives or anywhere. Whenever you have a radical, I'll write only inside as positive, whether this is odd radical or even radical. So, see the difference on the domain? You can clearly say, hey, there's no difference on the domain. They're all for positive numbers only. You can say that kind of thing and get away with it. Another feature is, slopes, steepness versus flatness. Square root is like that. And cubing root, it's closer to vertical, and then even more close to vertical around 0. And it's even more vertical around 0. You can see that kind of thing. And it is the opposite behavior of the nth power function, and grows much flatter when n is big, but here x and y are reversed. So flatter if you look at it from down here. So if you turn it around, then then x-axis and y-axis are changing. So we have more vertical, previously more horizontal, that kind of thing. I'm not going to go too deeply into that. Next example, power function, when the power is a negative integer, depending upon whether that negative integer is even or odd, you're going to get an even function or odd function. So 1 over x, when x to the negative first power, 1 over x squared, no, 1 over x squared is down here. That's even, x to the negative second power. This one is 1 over x to the third power, x to the negative third power. And this one here is x to the negative fourth power. Odd for blue, even for green. And we already explained the reason why we have that kind of symmetry. Even kills off negatives, so we have symmetry about the origin. Odd keeps the negatives, so if I keep negative, flip negative both x and y, then we have a symmetry about the origin. And another important aspect is we have vertical asymptotes around 0, getting closer and closer and closer, but not actually touching the vertical line. Horizontal asymptotes too. The x-axis is becoming the horizontal asymptote, getting closer and closer and closer, but never actually becoming 0. And you can see those kind of things through computation. Especially for horizontal asymptotes, we already went through those behaviors, so I don't think I have to spend a lot of time, but for vertical asymptotes, let's talk about it. For 1 over x squared, 1 over x cubed, consider plus or minus 0.1, 0.01, 0.001 like those. And then if you take reciprocals, we get 10, 100, 1,000 like that. So no wonder it's blowing up to infinity. And then negative infinity, because for odd power, negative stays at negative. But if you square those two observations, squaring the plus or minus, so negative will be gone, so we're always positive. So either way, positive side, negative side, they both go to positive infinity in terms of y-coordinate. They both go up. Here we have split, go up, here go down, here both go up. That's because even power kills off the sign. And another aspect is, look at those end results. Instead of 10, 100. Instead of 100, we have 10,000. Instead of 1,000, we get 1,000,000. Green graph is growing much faster to infinity. And this blue is growing even faster to infinity. This one, even faster than that. As n value gets bigger and bigger and bigger, as we move close to 0, the function value will blow up to infinity or negative infinity more quickly. And plus or minus will just disappear for even, stay, and consequently we have splitting behavior, one positive, one negative infinity for odd graphs. Now as for the horizontal asymptote, those are much easier. The properties of signs, they're going to go to 0 anyway. You look at all those 0.000 thing is. So they all go down to 0, so y-coordinates getting closer and closer and closer to 0, even though not precisely 0. So we have horizontal asymptote where y equal to 0, or the x-coordinate axis. So that's the power function number 3. And number 4 is the most general case, but I don't think it's worthy of our class time. It is just combination of b and c put together, or a, b, and c put together. If you have m over n power, then actually m power and then nth radical. We already talked about radical. And as for the powers, if it is positive power, we discussed in A. If it is negative power, we discussed in C. So we can have various situations. So we can rewrite all kind of radicals and denominators and things into power form. And that's going to be important in calculus. But for now, I don't see any kind of use. So please do not completely forget about those power functions and all possible cases in case you have to take calculus 1, which I think most students are taking. But for now, let's focus upon the graphs.